Today we're going to start talking about score-based models or diffusion models, and we're going to see that which is kind of like a state-of-the-art class of generative models for images, video, speech, audio, a lot of different kind of continuous data modalities. This is the way to go, and we'll see it's going to build on some of the techniques we talked about in the last lecture. So first of all, usual picture here, kind of like the overview of what we're talking about in this class. We talk a lot about different kinds of model families, and we've seen kind of like two main classes of generative models. We've seen likelihood-based models, where basically the key object you're working with is the probability density or the probability mass function. So the model is basically just a function that takes as input some x and maps it to some scalar, which is how likely is that x according to the model. And we've seen that probability mass functions or probability density functions are tricky to model because they have to be normalized. They have to integrate to one. So we've seen that one way to get there is to use autoregressive models. Another way to get there is use flow models, but that sort of always constrains the kind of architectures you can use. And the alternative way to go around it is to sort of like, well, give up some sense on the normalization and use variational tricks to essentially evaluate the likelihood. So we've seen variational autoencoders, and we've seen energy-based models where you have to deal with this normalization constant that normalizes the probability density. And we've talked about a bunch of techniques to kind of like try to get around the fact that you have to evaluate z theta and maybe avoid likelihood-based training and various ways of training energy-based models. And then the pros here is that you can do maximum likelihood training, which is principled, is great. It's a loss that you can monitor. You can see how well it goes. It's optimal in a certain sense. You can compare models, but you kind of have to deal with the restricted architectures. You can't plug in an arbitrary neural network to model the likelihood. The alternative way to go about this is to just model the sampling process. So this is kind of like an implicit generative model, like a GAN, where we're just going to describe the way you produce samples. For example, you feed random noise through a neural network. Essentially, any neural network you can pick as the generator defines a valid sampling procedure. The problem is that given a sample, given an output from this network, evaluating how likely the model is to generate that is very hard. And so you kind of have to give up on likelihoods again. And although these models tend to work pretty well, the key problem is that you can't train them in a very stable way. You have to do minimax optimization, and that's a problem. And so what we're going to talk about today is a different way of kind of like representing probability distributions, probability densities that deals with the score. Right? That's what these models are going to be. They're called score-based generative models, and this is only going to be applicable to probability density functions, so continuous kind of random variables. But when we're dealing with continuous random variables, then we can start thinking about working with the gradient of the log density instead of working with the density itself. And so, we've seen that in a likelihood-based model, you would normally work with P of x. And in a score-based model, instead, the object that you work with is the gradient of the log density. And the gradient, again, is with respect to the inputs. It's not with respect to the parameters of your model. And that's the score function. And we've seen this in the previous lecture, but kind of like the idea is that it provides you an alternative interpretation of the probability density function. You can alternatively think of the PDF as a function that maps every point to a scalar, which is non-negative. So you can think of it as the height of some kind of surface over this 2D space. In this case, it's a mixture of two Gaussians. And the score is just a function that is vector valued. At every point, it gives you the gradient of the log density. And so it's this kind of like vector field where at every point you get the arrow is telling you what's the direction that you should follow if you want to increase the log likelihood most rapidly. And these two are sort of like equivalent views. So if you like, again, analogies with physics, this is kind of like describing a physical system in terms of electric potentials or electric fields. They're kind of like the same, but computationally it might be advantageous, as we'll see, to work with one versus the other. And in particular, kind of like the main challenge that we talked a lot about in this course when modeling probability density functions is that you have to make sure that these PDFs are normalized. So you kind of like need to figure out a way of parameterizing curves that are ideally flexible, in the sense they can have arbitrary shapes as you change, or as complicated as possible of a shape as you can get by changing the parameters of your neural network, but somehow you need to make sure that the total area under the curve is fixed, it's equal to 1, so you have a normalized object, or some way of somehow computing the area under the curve for any choice of the parameters, and that's potentially tricky, as we've seen. Often what it means is that you have to choose very specific architectures that allow you to basically either guarantee that the area under the curve is 1, or somehow, like in a normalizing flow, that you can compute it efficiently. And now if you think about the score, in the 1D case, the score is just this is the gradient, is the derivative of the function you see of the log of the function you see on the left. And the function on the right no longer needs to satisfy any kind of like normalization constraint. So, and it's potentially much simpler to sort of like work with. You see here, I have this relatively complicated curve on the left, and the corresponding score function on the right is potentially much easier to work with. So kind of like the intuition behind a score-based model is that instead of modeling data using the density, we're going to model data using the score. So that's going to be the object that we're going to use to define our model family. And we've seen that this is useful in the context of energy-based models. Energy-based models are one way of defining very flexible kind of probability density functions by saying, okay, I'm going to pick an arbitrary neural network, I'm going to make it non-negative, and then I'm going to renormalize by dividing, somehow computing the total area under the curve and then dividing by that number to get a valid probability density function. Super flexible. The problem is that if you want to do kind of like evaluating likelihoods involve the log partition function. So if you want to do maximum likelihood training, you have to go through either somehow estimate a partition function, or you need to do contrastive divergence kind of things where you have to sample from the model, which is expensive. On the other hand, which is something you don't want to do, on the other hand, what we're seeing is that we can train energy-based models by matching, instead of trying to match basically the density ratios using KL divergences, we can try to fit our energy-based model by trying to make sure that the corresponding vector field of gradients, so the scores of the model, match the scores of the data distribution. And so, recall that this was basically the Fisher divergence, and we were able to do, through integration by parts, we were able to rewrite this objective function into one that basically only involves the score, which, as we've seen in the last lecture, does not require you to compute the partition function. So the score here, the critical thing to notice here is that the score function, the gradient of the log density according to the model, when you take the log of an EBM, you get your neural network, and then you get the log partition function. Critically, the log partition function does not depend on x. It's the same for every point. It's just the area under the curve. So no matter where you are, the area under the curve is the same. And so when you take the gradient with respect to x, that's 0. And so we can compute this model score in terms of the original energy of the model. And so in this expression here, we can basically compute this term efficiently without having to deal with the normalization constant. And so we have this sort of like expression. If you want to do score matching for an energy-based model, you have that loss, which you can in principle optimize and try to minimize as a function of theta. And now you might wonder, I mean, can we only do score matching for EBMs? And if you think about it, it's if you look at the laws, it's something that is well defined for any model family. Like as long as you're able to compute this gradient with respect to x of the log density according to the model, then you can do score matching, and you can train a model by minimizing the Fisher divergence. And so in particular, what other kind of model families can we apply score matching to? Well, we can certainly apply it to continuous autoregressive models. If you can compute the log density, you can probably also differentiate through that and compute the score. You can do it on normalizing flow models. Again, we can compute the log likelihood, and so we can also compute the score. Although perhaps it doesn't make a lot of sense because you have access to the likelihood, so you might as well train these models by maximum likelihood, but in principle, you could apply score matching to these models and you could train them that way as well. So, but you could also wonder, I mean, what's the most kind of like general model family that we can train using score matching? And you can kind of think that, well, you can certainly apply it to autoregressive models, to flow models. You can think of EBMs as kind of like a generalization where, autoregressive models and flow models are special kinds of EBMs where the partition function is guaranteed to be 1. But perhaps there is something even larger, like we can even optimize over an even broader set of model family. And that's kind of like the idea behind a score-based model. Like instead of modeling the energy, we're basically directly going to model the score function. So we're going to define our model family by basically specifying the corresponding vector field of gradients. So the model is not going to be a likelihood, the model is not going to be an energy, the model is going to be a vector valued function or a set of vector valued functions. As you change theta, as you change your neural network, you're going to get different vector fields. And that's what we're going to use to describe basically the set of possible distributions that we are going to be fitting to a data distribution in the usual way. And so basically the difference with respect to an EBM is that we're not going to model necessarily the energy and then take the gradient of it. Instead, we're going to directly think about different kinds of vector fields that we can get and we can parameterize using a neural network. And in this case, the neural network is a vector valued function. For every x, s theta, the estimated score at that point is a vector with the same number of dimensions as the input. So s theta is really a function from RD to RD. So if you have d dimensions, the output of this neural network will also have d dimensions because that's however many coordinates you need to specify one of these arrows at every point. And so that's basically the kind of very high level story here. As usual, we want to fit a model to a data density. So there is a true underlying data density that is unknown. We assume we have access to a bunch of samples from the data density. And then what we're going to try to do is we're going to try to find some function in our model family. So we're going to try to choose parameters theta, or we're going to try to choose some vector field of gradients that is hopefully as close as possible to the vector field of gradients of the original data density. So that's going to be kind of like the learning objective. We're going to try to choose parameters theta such that the corresponding vector valued function that we get matches the true vector field of gradients of the data density.
How can we make sure the gradients calculated from the sparse samples as close as to the underlying distribution of our data?
Yeah, so that's a great question. I mean, the only thing we have access to are samples, and so we don't have access to the true density, and so we're never going to be able to achieve this perfectly. And there is a learning element in the sense that we only have access to a bunch of samples, and so we need to make sure we're not overfitting, and we need to make sure that there's going to be some limits to how well we can do this. But it's that you have the same problem even if you have if you're training by maximum likelihood. You're only given samples. You can try to get as close as possible to the empirical data distribution, hoping that by fitting the samples, you're also fitting the true underlying data density. So we're going to have the same problem in the sense that we only have samples, we have limited data. But the main difference is that instead of trying to fit one of these this scalar function that is giving us the likelihood, we're going to try to fit this vector valued function that is giving us the gradient of the log likelihood, essentially. Yeah.
Sort of building off that, but so for instance, over here we have like 2 clusters, right? But in but we want a model to be able to predict even like in the sort of decision boundary of the score and all these sorts of things. But isn't that too much of an OOD problem? Like, I know you said that, okay, even when you're going for the likelihood, it's fine, but when you're going for the likelihood, you're sort of within reasonable range if you're trying to sort of push PMF like close to the where your samples are. Here you're sort of learning like, okay, I have some data here and I have no other data and some like valley, and I'm yet somehow expected to learn some.
Yeah, so I think in both cases it's a hard problem. Like I would say that even if you work with likelihoods, you don't just want to put probability mass around the training data because you want the model to generalize to unseen data that it hopefully coming from the same distribution as the one you've used for training, but you don't want to just fit the the training distribution. Right? If you're fitting a model over a training set of images, you don't just want to put probability mass around the images that you have in the training set. You want to spread it out, and you need to be able to say, oh, there is other parts of the space where I need to put probability mass, even though I have not seen them during training. And so we have a similar problem. To some extent, kind of like the gradient and the function are essentially the same thing. So if you have the gradient, you can integrate it, and you can get the function. And because everything has to be normalized, so you know that you can get the function up to a constant, and we know what the value of that constant needs to be because it has to be normalized. So in some sense, it's just as hard as the original problem.
As far as overfitting is concerned, I think it will be strongest in this, right, compared to other models we have seen, because what do you think?
Depends on the loss that you use. As we'll see, there's going to be issues that are very specific to training with the Fisher divergence. That makes it so that kind of like doing things, this vanilla sort of like approach will not quite work, and we'll need to do a bunch of different things to actually make it work in practice. But so far, it's more like up to here, I'm just saying it's going to be a different representation of the kind of models we are willing to consider. I haven't even said how are we going to do the training and how do we prevent overfitting and so forth.
I'm wondering how are energy-based models not a generalized kind of a model for score matching? Because from my understanding, if you're using training by like Fisher divergence, you don't estimate the energy or the partition at all. You just look at the scores, and
yeah.
How is that not a generalized?
So the idea would be that potentially the vector field that you model might not be the gradient of a scalar function. So it might not necessarily be a conservative vector field. So you can imagine that here, if you do things this way, f theta is a scalar function, which is kind of like the potential. If you think about it in physics term, like there is a potential, maybe an electric potential, and that's a scalar. And you get the vector field by taking the gradient of that. So it's a way of parameterizing a set of vector fields that they need to satisfy certain kind of properties because they are the gradients of a scalar function. Here I'm saying, oh, I'm no longer even going to restrict myself to gradients of scalar function. I'm going to allow myself to just have arbitrary vector fields. There might not be an underlying scalar function such that this vector field is the gradient of that function.
So we're just modeling all gradients. We're not having any functional parameters.
Exactly.
So building on that question, is it fair to say that in the energy-based model, we still try to model directly like the likelihood, versus here we directly model the scores, which are the gradients?
Yes. Maybe.
Are we missing the VAE for a specific reason? Is that on?
VAE is not technical in EBM because you don't even get the, there is no normalization constant, and that the likelihood comes from an integral because of the latent variables. It's not directly something that would fit here.
I think I was just wondering, like, there seems to be like some semantic overloading. Like, why do we call this like scores and not just like gradients? Like, why, do we have different terms meaning the same thing?
They're just, the reason they're called scores is that they're called scores in the literature, and people use score matching for the losses, and it's called the Fisher score, and that's why we chose that name. Yeah.
What's the cost of looking at the gradients? Because then if there's nothing, then we can just look at the second derivative, the third derivative. Like, why can't we just keep going?
You could. Yeah. Although I haven't seen it done, but in principle, you could potentially look at. Maybe it's going to be too high dimensional, too complicated, but you could.
Well, if the gradients aren't with respect to like DFX, how do we expect to like generate?
Yeah, so we'll talk about how to do inference, how to do sampling, and those kind of things.
I want to kind of go back to when you first talked about the score matching a bit, like why score matching will kind of lead to identical or just to this distribution, like the PDF be similar. Because like for the score matching, if we think about it, it's kind of like the gradient of the PDF, right?
Yeah.
And then we do integrations, but how about the constant terms that will?
It has to integrate to 1 because it's the density.
Okay.
So if you integrate a function, when you integrate, you get the function up to a constant, and that constant is determined by the fact that the integral of the PDF has to be 1. So there is no loss of information. In general, when you go from a function to the derivative, you lose information about a shift, basically, because you can't recover the, if you take a function and you shift it by a constant, they will both have the same derivative, right? So it looks like you lose information. But here you don't, because we know that the functions have to integrate to 1. Cool. So that's sort of like the high-level idea. We're going to try to fit directly score models to data. So the problem is this: you're given IID samples from a data density, which is unknown, usual learning setting, a training set of samples from some unknown data distribution, and you want to try to estimate the score of this data distribution. And so we're going to think of a model family, which is going to be a set of vector-valued functions parameterized by neural networks. As you change theta, you change the shape of the vector field. And the goal is to choose parameters so that the vector fields are similar. So you can imagine the first question is, how do we compare two vector fields? So there's going to be kind of like the true vector field of gradients corresponding to the data density. There's going to be an estimated vector field of gradients. How do we compare them? A reasonable way to do it is to basically overlap these two vector fields. At every point, there is going to be a true gradient, an estimated gradient, and we can look at the difference between the two and average this over the whole space. And if you do that, you get back the Fisher divergence that we talked about before. Right? So if you go through every x, you look at the true gradient at that point according to the data density, you look at the estimated gradient at that point according to the model. There's going to be some difference. You look at the norm of that vector, you average with respect to the data density, and that's going to be a scalar value that tells you how far away your model is from the true vector field of gradients of the data distribution. So if you can get this quantity to 0 as a function of theta, then you know that the vector fields match, and you have a perfect model. And so trying to minimize this as a function of theta is a reasonable learning objective. And we know that even though it looks like something that you cannot possibly optimize because it depends on this unknown quantity here, recall we only have access to samples, we can do integration by parts and you can rewrite it in terms of an objective that only depends on your model. And it still involves an expectation with respect to the data, but you can approximate that using a sample average. So in order to train this kind of model, you need to be able to evaluate S data efficiently. And we need to somehow be able to compute this trace of the Jacobian, which is basically the sum of all a bunch of partial derivatives. And then there is the question of, well, do we need this core model to be proper, to correspond to the gradient of some energy function? And we'll see that that's actually not really needed in practice. So the most straightforward way of kind of parameterizing the score would be to just pick a vector value, the neural network. So let's say you have 3 inputs and 3 outputs. Because we know at every point, this neural network has to estimate a gradient, which is a vector, which is the same dimension as the input. And then we need to be able to basically evaluate this loss, which involves the norm of the output of the neural network and the trace of the Jacobian. And so to evaluate the first term, which is just the norm of the output, it's easy. Basically what you do is you just do a forward pass, and then you can compute S theta, and then you can also compute the squared norm of S theta. The more complicated piece is the trace of the Jacobian. So the Jacobian is basically this matrix where you have basically all the partial derivatives or all the gradients of every output with respect to the inputs. So the first term up here is the partial derivative of the first output with respect to the first input. And then you have all these partial derivatives that you have to deal with. And the problem is, we're trying to compute the trace of this matrix, which is basically the sum of the elements on the diagonal. And so what you need to do is you need to be able to compute the partial derivative of the first output with respect to the first input. And then you need to compute this element here on the diagonal. You need to compute the partial derivative of the second output with respect to the second input. And then you need to compute the partial derivative of the third output with respect to the third input. Then you have to sum up these 3 numbers. Because you need to sum up the elements on the diagonal of this matrix. And although we can do backpropagation, so you can compute these derivatives relatively efficiently, naively doing this would require a number of backpropagation steps that scales linearly with the number of dimensions that you have. And we don't know if there is a more efficient way of basically doing this, but the only way basically we know how to do it is essentially extremely inefficient when the number of dimensions grows and is very large. And so even though this loss does not involve partition functions, it still scales pretty poorly with the dimensionality of the data.
Doesn't ebms have the same problem? Like we also have to calculate the trace of the Hessian.
Yeah. So EBMs are even worse because in an EBM you would need to do one more backprop to get the score, and then one more to get these derivatives. So an EBM would even be even more expensive. This at least saves you one backpropagation because you're already modeling the gradient of something, but it's still expensive. Yeah.
I thought in EBMs it reduced to F theta.
Yeah. So you have the Hessian of F theta. So when you take the first gradient with respect to x, of f theta, you get essentially s theta. And then you have to do the Jacobian of s theta. And so you need to do second order, basically, derivatives in that case. So it's even more expensive.
Do the input and output dimensions have to be the same, or can you use different ones?
They have to be the same here because you're modeling the score, which is the gradient of the log likelihood, and so that has to be the same dimension as the input. Yeah.
Do you have to? Oh, I guess you're trying to match with the gradient, so then yeah. Okay. So like, does this method only deal with the data that has the same dimensions, right? Because we're trying to basically compare the scores at each points, right? So we can only deal with the data that it has with the identical dimensions.
Yeah. So this is we're modeling a joint distribution over a set of random variables, and if some of them are missing, computing marginals might be expensive. Yeah. Cool. So this vanilla version, which is something we briefly mentioned also in the last lecture, if you recall, we said, okay, this avoids the partition function, but doing integration by parts is still expensive because of this Hessian term or trace of the Jacobian in this case. And so we need more scalable kind of approximations that work in high dimensions. And that's kind of like what we're going to talk about next, which is how to get this to scale to high dimensional settings, where basically this D is large. And there's kind of two approaches that we're going to talk about. The first one is called the denoising score matching. And the idea is that instead of trying to estimate the gradient of the data, we're going to try to estimate the gradient of the data perturbed with noise. So you can imagine that there is a data distribution that might look like this, and then there's going to be a noise perturbed data distribution shown in orange, denoted Q sigma, where we're basically just adding noise to the data or convolving kind of like the data density, in this case with a noise distribution, Q sigma of x tilde given x, which might be something like a Gaussian in this case. We're kind of like smoothing the original data density by essentially adding noise. And then it turns out that if you estimating the score of this distribution that you get after adding noise is a lot easier computationally. And so to the extent that you choose the noise level to be relatively small, this might be a reasonable approximation. So kind of like if you don't add too much noise, then this yellow density will be pretty close to the blue one. And so the scores that you estimate for the yellow density, the noise perturbed density, are going to be pretty close to what you want. And so because basically Q sigma is going to be pretty close to the original data density when sigma is small. That's the high level idea. And so kind of works like this. You have a data density, which could be over images. And then you add noise to the images by using this Gaussian kernel, Q sigma. And then you get a new distribution over images plus with noise. And we're going to try to estimate the score of that. And the way we're going to try to fit our model to this noise perturbed data density is again using the Fisher divergence. But now, instead of doing Fisher divergence between model and data, we do Fisher divergence between model and this noise perturbed data density. So it's the same thing as before, except we replace p data with Q sigma, which is the same as, which is data plus noise, basically. And then, which is just this. So the expectation is just this integral with respect to Q sigma. So just like before, it's just the norm of the difference between the estimated gradient and the true gradient, except that now instead of using the real data density, we use this Q sigma, which is the noise perturbed data density. And then we do, just like kind of like when we're doing integration by parts, we expand this square and get three terms. We get this the norm of the first term, the norm of the second term, and then we have this inner product between the two pieces. The red term, which is going to be the complicated one. Basically, just like in the integration by part kind of trick, you can see that the blue term does not depend on theta, so we can ignore it. The green term depends on theta in an easy way. So it's just basically the usual thing. And the complicated piece is the red one, where we have this dot product between the score of the noisy data and the estimated score. Yeah.
Could you describe again how you're sampling from Q? Are you first formally sampling the data and then?
Yeah. So Q is defined as basically you can get a sample from Q sigma by randomly drawing from the data, randomly drawing some Gaussian noise and adding it to the data. Yeah. Other questions? Yeah.
What does this Q give us? Like, what do we achieve by it?
So we achieve that it's going to be tractable in the sense that we're going to get rid of that trace of the Jacobian term. So we're going to get a loss function that is going to be scalable in high dimensions. So that's going to be we're doing this because the trace of the Jacobian was too expensive. This introduces an approximation because you're no longer estimating the score of the data density, you're estimating the score of this other thing. But it turns out that we're going to be able to do it much more efficiently. Yeah.
Wouldn't that gradient somehow still depend on the gradient with respect to x?
Yeah, it looks like it does, but then it turns out we'll see that it actually simplifies to something pretty intuitive and very simple. It's gonna reduce this problem to denoising. So basically, this score matching like objective will end up being equivalent to the problem of given this x tilde, try to remove noise and try to estimate the original image you started with, basically. It's going to be mathematically equivalent. Basically, we're going to rewrite this red term in where do I have my cursor here? We're going to rewrite this red term in some way, and we're going to show it's going to be equivalent to denoising. So, okay, so we ignore the blue term, it doesn't depend on theta, then we have this green term, which is easy, and then we have this red term, which is tricky, but we're going to rewrite it. So, focusing on the red term, it looks like this, and just like in the integration by part kind of trick, we can write the gradient of the log as 1 over the argument of the log times the gradient of the argument of the log. This is the basic. I just basically expanded the gradient of the log of Q sigma. And now you see that this Q sigma here and Q sigma down here will cancel with each other. And so we end up with something a little bit simpler. It's just the dot product basically between the gradient of the noise perturbed density and the gradient and the score model at every point. And now we can write the expression for Q sigma, which is just this integral. Basically, the probability of any particular sigma, x tilde, is going to be the probability of sampling any data point x times the probability of generating x tilde by adding noise to x, basically. That's just if you think about the sampling process, what is the probability of generating an x tilde? You have to look at every possible x, and you have to check what was the probability of generating x tilde by adding noise to x. And that's basically what this integral here is giving you. It's just the definition of Q sigma that we had in the previous slide. And now we can see that this is linear, and so we can push the gradient inside the integral. And that's where things become a lot simpler, because now you see that now we are getting a gradient of this Gaussian density, basically, and we no longer have to deal with the gradient of the data density, basically. And now we can further push out the, well, now we can use the, again, this trick here that the gradient of the log of Q is 1 over Q times the gradient of Q, and we can rewrite the gradient of the transition of the Gaussian density as Q times the gradient of log Q. Because if you take the gradient of log Q, you're going to get the gradient of Q times 1 minus Q, and so these two things are obviously the same. And now you push the expectation out, and we basically have an expression that looks very much like the original one that we started with, but we no longer have to deal with this gradient of the log data density perturbed with noise, but we have to look at the gradient of this conditional distribution of x tilde given x, which is just a Gaussian density. And so overall, basically we've rewritten this complicated object up here into something that is a little bit simpler, because now it involves only the gradient. It basically involves the score of this Q sigma of x tilde given x, which is just going to be Gaussian. And so bringing it together, this is what we started with, estimating the score of the data density perturbed with noise. We know it, you could write it this way, and through this algebra that we just did, we could also rewrite the red term in terms of this. And now you can basically see that essentially, you can write it as the square difference between S theta and the gradient of this Gaussian transition kernel that we have here, because that would give us, when you take the square of this term, it would give you the red one. The square term of this one will give you this brown term that then we're subtracting out. And then the dot product between these two is exactly this red term that we just derived. So all in all, basically, what we've shown is that if you want to estimate the score of the Q sigma, the noise perturbed data density, it's basically equivalent to trying to estimate the score of this transition kernel, this Gaussian density that we use to add noise across different x's and different x tildes that are sampled from the noise distribution. So a lot of algebra, but basically up to constants, we can rewrite the score matching objective for the noise perturbed data density into a new score matching objective that now involves terms that are relatively easy to work with. And in particular, if you look at this expression, it turns out that this gradient of the log of Q sigma x tilde given x is easy to compute because that's just a Gaussian. So Q sigma x tilde given x is just a Gaussian with mean x and standard deviation and variance sigma squared the identity. So that's just squared exponential. When you take the log, it just becomes a quadratic form. When you take the gradient, you just get a relatively, basically, an expression that looks like that. And so when you plug in this expression in here, you get something easy to work with. Maybe I don't have it here, but basically you end up with an objective that no longer involves traces of the Jacobians. It's kind of like an L2 loss between S theta compared to this x tilde minus x over sigma squared, which is basically a denoising objective, as we'll see in the next couple of slides. So the key takeaway here is you don't have to estimate the trace of the Jacobian anymore if you're willing to estimate the score, not of the clean data, but if you're willing to estimate the score of this Q sigma, which is data plus noise. And so practically, the algorithm is something like this. You have a mini batch of data points sampled from the data. You perturb these data points by adding Gaussian noise. So literally just add noise to each xi with the variance sigma square. And then you just estimate the denoising score matching loss, which is just based on the mini batch, which is just the loss on these data points, and it's just basically this expression. And recall that if this Q sigma is Gaussian, then the loss looks something like this. And so it has a very intuitive kind of interpretation, because what we're saying is that what the score model needs to do at every data point, x tilde. So the score model is being evaluated at these noisy data points, x tilde. And for each data point, what the score model is trying to do is it's trying to estimate the noise that was added to xi to produce x tilde.
Do we have some restriction on like how noisy, like how large let's say the standard the sigma here where we're trying to kind of add noise to the arrangement?
Yeah, so you'd want sigma to be as small as possible because you want Q sigma to be as close as possible to P data. On the other hand, the variance goes to infinity of this loss as sigma goes to 0. So you can't actually choose sigma to be too small. And so in practice, you need to try to choose the sigma as small as possible, such that you can still kind of optimize the loss. But there is always an approximation. So that's the trade-off. You don't have Hessians or traces of the Jacobian anymore, but you're not estimating the score of the clean data, you're estimating the score of the noisy data.
I understand like it's a little different, but like the gain here, we get rid of the trace of the derivative of the scores is because we know the closed form sequence of the noise that would happen.
Yeah. We're no longer estimating. I mean, we're changing the goalpost. We're no longer estimating you can think of this as basically a numerical approximation of, in some sense, like we're adding Gaussian noise and we're trying to estimate derivatives through kind of like a finite difference kind of thing. Basically, that's one way of deriving the same thing. If you like that sort of approximation route, it has the flavor of basically estimating the derivatives through a perturbation.
Why is it denoising score matching? Because we're matching to a perturbed data point, right? How does it help with denoising?
So if you think about when is this loss 0? Maybe that I have it on the next slide. Yeah. So like if you think about it, the loss function looks like this. The original loss function was this, and then we were able to rewrite it as this. And so what are you doing? You're starting with a clean image, then you add noise to generate x tilde, then look at this loss. What we're saying is that the score model takes x tilde as an input, and to make this L2 loss as small as possible, you're trying to match this x minus x tilde, which is exactly the noise that we added. And so to make this loss as small as possible, S theta has to match the vector of noise that we added to this image. And so that's why it's a denoiser, because it gets to see x tilde and it needs to figure out what do I subtract to this x tilde to get back a clean image.
Because even though we're not directly comparing with the original image, we still somehow manage to.
Yes, that's called Stein unbiased risk estimator. That's the key trick that is used. You can still evaluate the quality of an estimator without actually knowing the ground truth in some sense. Yeah.
So do I understand correctly that the only unknown in this optimization is basically the theta? Like you have basically the x tilde, the sigma, basically everything except for the theta, right?
Yes, so the x's and the x tilde, you're generating them yourself, but S theta doesn't see the clean data. So X theta only sees the noise data, and then you're trying to predict the noise. Yeah.
Yeah, so since like after we added this Gaussian distribution perturbation, the S is trying to basically match the gradient of that Gaussian noise distribution, but the training goal was this as score function should be the gradient of original log likelihood of the original data distribution. So it seems that this trained as deviates from the original goal. For example, if we, instead of using Gaussian distribution to add the perturbation, if we use another noise distribution, that basically changes the loss function for as and gives a different as. Is that what's happening?
You could, yeah. So it's not restricted to Gaussian noise. Like if you look at the math, the only thing you need to be able to compute is this gradients of basically as long as the distribution that you use to add noise, that you can compute likelihoods and you can get the gradient in closed form, then you can get a denoising like loss for that. You're gonna end up estimating the score, like we are estimating the score of Q sigma, right? Which is, if you're adding Gaussian noise, it's gonna be basically data plus Gaussian noise. If you add another kind of perturbation, you're gonna get another kind of type of data, perturbed data, and you're estimating the score of that. So you're right, like we're not estimating the score of the clean data density, we're estimating the score of the data plus noise. The hope is that you need to add just a small amount of noise so that kind of like if sigma is small enough that these images are indistinguishable from the clean ones, then the approximation is not too bad. And what we gain by doing that is much more scalable.
Because it feels like instead of converging to the distribution of clean data plus noise, it gives me the feeling that we're converging to the distribution of the noise function.
It doesn't. No, that's the key thing. So you are still, if these two, even though, I mean, that's the magic of denoising score matching, that basically these two objectives are equivalent up to a constant. So by minimizing the bottom one, the denoising, you are actually also minimizing the top objective where you're really estimating the score of the distribution of the data convolved basically with Gaussian noise, the smoothed version of the data density. Even though you can just work at the level of the individual conditionals. That's kind of like the beauty of this denoising score matching.
Maybe taking a step back, the whole premise of this approach is that it is easier to model the basically vector field of gradients than the probability distribution directly, right?
Yeah. And another way to say it maybe is that denoising is not too hard as a problem. And so we have pretty good neural networks that can do denoising. And so to some extent, we've reduced the problem of generating images to the problem of denoising, which is a relatively easy task for a neural network. So to the extent that you can do well at denoising, you're going to do well at estimating the score. And we know that the score is basically, to some extent, equivalent to having a likelihood. So we haven't yet talked about how do you actually generate samples from these models, but essentially we'll do MCMC. And so after all these steps, we've reduced generative modeling to denoising, which is an easy task, probably one of the easiest tasks that you can think of.
So is this like some like coincidence that getting the gradient this turns out to be this denoising objective that only people like Gaussian or this checkout beautifully exists? There's some underlying thing that leads to this.
So it doesn't have to be Gaussian as long as the machinery, basically as long as you can compute this gradient of the whatever distribution you use to add noise, the math works out. And really, if you think about what happened in the proof, the only thing that matters is that the gradient is linear. The gradient is a linear operator, and so this whole machinery works.
So I'm looking at the estimation, the optimization objective. So if we are doing optimal optimizations, the score function should be close to the noise over divided by the standard deviation we chose, and it should also be close to the actual kind of gradient of the of Q.
Yeah.
R. So are we claiming that the gradient of the disturbed image should be similar to the noise?
So let's see in to what extent that that is true. So here we've seen that score matching reduces to denoising. So estimating the score is the same as estimating the noise that was added to the data point. And so the reason this is true, or another way to think about this, is that there is something called Tweedy's formula, which is basically an alternative way of deriving the same result, which is kind of like it's telling you that indeed, kind of like as was suggested by you, that the optimal denoising strategy is to basically follow the gradient of the perturbed log likelihood. And so you can kind of imagine that if you had a data density that only has kind of like three images, so it's kind of like 3 deltas. This is kind of like a toy picture, but just for visualization purposes, you can imagine that if you add noise to these 3 images, you're going to get a density that kind of looks like this. And then you can imagine, let's say you're trying to denoise. And what we've just shown is that kind of like the best way to denoise is to follow the gradient. So if somehow somebody gives you a data point to the left here, how should you denoise it? You should follow the gradient to try to go towards high probability regions, which kind of makes sense. If you're trying to denoise, try to change the image and push it towards high probability regions. And in fact, the optimal denoising strategy is to take the noisy sample and follow a step, plus with the right scaling, but basically follow the gradient of the log perturbed data density.
Is it kind of based on the assumption that the expectation of the noise is 0 or something like that? Like
it doesn't even
does not. Yeah.
I mean, there must be some sort of, like you said, must be gradient there must be like some sort of constraints on the noise, right? Because if I can consider coming up with noises where the gradient might not be the optimal, like taking the gradient might not be the optimal.
So for this result, the denoising score matching stuff, it's still true. What it's good about Gaussian is the following. Maybe that will clarify. So essentially, what you can look at is, there is the data, clean data, and then there is the noisy data, and then there is the posterior distribution of the clean data given the noisy data. And we know the definition of the noisy data distribution, and basically Tweedy's formula is telling you that the expected given a noisy image X, the expected value of the clean image is given by this expression. And so if you want to minimize the L2 loss, the best thing you can do is to output the conditional expectation of X given X tilde. And so from that perspective, you want to follow the gradient. And this particular version of the formula is only true for Gaussians.
You just give it noise until it denoise that. Is there a notion that would, if you keep denoising noise, what would happen?
So if you keep denoising noise, so are you asking if you have a lot of noise or if you keep repeating the process?
Yeah, you start with a bunch of noise and just keep letting it denoise it.
Yeah, so that's going to be basically how we sample from the model. So that's going to come up soon. But essentially, that's how we're going to keep following the gradient, or equivalently kind of keep denoising. And there's going to be MCMC in some sense, and that's going to be Langevin dynamics, and that's how we're going to produce samples, basically.
This is how kind of diffusion models are.
Yeah, exactly. Cool. So the other way to make things efficient is to take random projections. Maybe I still have time. So another alternative way of kind of coming up with an efficient approximation to the regional score matching loss that does not involve kind of traces of the Jacobians is to basically take random projections. So you can imagine at the end of the day, what we're trying to do is we're trying to match the estimated vector field to the true vector field. And if if these vector fields are really the same, then they should also be the same if we project them along any kind of direction. So you can take this direction, and you can project the arrows along that direction. And if the vector fields are the same, then they should match. The projections should match. Right? So in particular, if these projections are just axis aligned, then individual components of these vectors should match. And the idea is that working on the projection space is going to be much more efficient because now it's going to be a one-dimensional problem. And so that's defines basically a variant of the Fisher divergence, which we call the sliced Fisher divergence, which is exactly what we had before. But before comparing the data to the model gradients, we project them along a random direction v. So you randomly pick a direction v, and then at every data point you compare the true gradient and the estimated gradient along this direction v. And note that after you take this dot product, these are scalars. So these are no longer vectors, they are scalars. And it turns out you can still do integration by parts, and you end up with an objective function that looks like this. And it still involves the Jacobian, but crucially now it involves basically Jacobian vector products, which are basically directional derivatives and are things that you can estimate using backpropagation efficiently. So the second term is just the usual thing, is efficient. It's just the output of the network times dot product with a random vector, so that's efficient to evaluate. Now we have something that looks like this. We have this Jacobian matrix, left multiplied by this vector v, and right multiplied by the same vector v. And it turns out that basically this thing is just like a directional derivative, and that's something you can compute with backpropagation efficiently. So if you think about it, this is the expression we started with, which you can equivalently write as the gradient of the dot product. And that's something that you would compute like this. So you have a forward pass that computes as theta. Then you take the dot product with v, and that gives you a scalar. Now you do a single backpropagation to compute the gradient of that scalar with respect to all the inputs. And then you take another dot product to get back the derivative or the quantity. And so this can basically be done roughly at the cost of a single backpropagation step.
I wonder, is the projection operation bijective? Or is it just like a vector dot product?
It's a dot product.
Dot product, I see. Yeah. So it's like the V is predefined.
The V is sampled from some distribution. Let me see if I have it here. So this is what it would look like. So you would sample data. For every data point, you would randomly sample a direction according to some distribution. And then you just optimize this objective function, which, as we've seen, is tractable to estimate, and it does not involve trace of the Jacobian. And there's a lot of flexibility in terms of choosing this PV, like how do you choose the directions. And you can choose, for example, Gaussian or Rademacher kind of vectors, and they both work in theory, and the variance can vary, but basically there's a lot of flexibility in terms of choosing the random directions.
So okay, with this one you can run one backprop. Why in the other case did we have to run multiple backprops?
Because you have to compute before you have to compute the partial derivatives of every output with respect to every input. Okay. So you needed d backprops. Okay. And here you can do a single one because it's basically a directional derivative. Yeah.
Does it ever make sense to bias the projections that you sample towards certain directions?
Yeah, it seems like intuitive. We tried it for a long time and never saw any difference in practice. I don't have anything conclusive to say. It seems like a good idea, but never worked.
So if you have like a high dimensional like output vector space, but then like if depending on the structure of that output space, like there are going to be certain directions where you have like a lot of signal, and then probably many more directions where you just don't have a lot of signal. And so it seems to me that like just picking like a projection vector from a Gaussian distribution like wouldn't work very well. Like you would get like, you know, some small amount of the time you would get, you know, a high value of this projection, but some other larger amount of the time you would get a projection where like your signal or your information was very, very low. And so I guess how does that sort of work out in training or in practice?
Yeah, so basically these are essentially unbiased estimators of the original objective. You can also think of it that way. There is variance that you're introducing because you're sort of like comparing projections of the vectors instead of comparing the vectors fully, which is what the original score matching loss would do. And so that's the price you pay, basically. And you can use variance reduction techniques to actually make things more stable in practice. Different distributions. Well, what you can do is you can take, if you are willing to pay a little bit more computation cost, you can take multiple random projections per data point. You can just try to match, not just sample v1, x1 along direction v1, but you can take a bunch of them and then average them. And so there is a natural way of reducing variance by taking more projections, but then it becomes more expensive. Eventually, if you take n projections, where n is the dimensionality, and you can kind of compare on every single coordinate, it goes back to the original one. And you are free to choose something in between. In practice, one projection works.
So is the idea why this doesn't take ON, OD time is that at each backpropagation step, we do the vector product and it becomes kind of one single.
Yeah, it becomes a scalar, yes. Exactly. Yeah.
Can we do all of this projection without worrying about noise?
Here there is no noise, yeah. So the advantage of this is that you are actually estimating the score of the data density as opposed to the data density plus noise. Yeah. And here you see some plots kind of showing that if you do vanilla score matching, how long it takes per iteration as a function of the data dimension. You know, it can go up to 300-400 dimensions, and then you run out of memory. This was a few years ago, but it kind of scales poorly, linearly with respect to the dimension. And if you have the sliced versions, they are basically constant with respect to the data dimension. And in terms of model quality, it actually performs. Not super important what this graph means, but it kind of like what you get with sliced versions of score matching matches pretty much what you would get with the exact score matching objective. Now, the final thing I wanted to talk about is actually how do we do inference? How do we generate samples? Like suppose that somehow we're able to, question.
Yeah, I just had one more follow-up question on this, like basically creating the scalar and then doing one backdrop. Like why do you do this with a random vector and not with like just a scalar product with the corresponding? So you have predicted this gradient, right?
Yeah.
And you know basically the gradient of the actual gradient, the ground truth gradient.
You don't know it.
But didn't we take like the L2 norm like previously?
Yeah, so you still need to do the integration by parts trick. So this one, you don't know it. So the original loss would basically just take, at every x, you take the dot product of the true gradient, the estimated gradient, and then you square the difference. That's still, you can't evaluate that loss because it depends on the true gradient, which you don't know. But then you can do integration by parts and you can rewrite it as this thing, which is kind of like what we had before, and it no longer depends on the true score. Yeah. Cool. So the thing I wanted to talk about is how to do sampling. So let's say that somehow you've used the real, like a vanilla score matching or denoising score matching or slice score matching, and you are able to train your neural network as data so that the estimated vector field of gradients is close to the true vector field of gradients of the data density. The question is, how do you use this, right? You no longer have access to a likelihood, there is no autoregressive kind of generation. How do you generate samples? And so the intuition is that the scores are basically telling you in which direction you should perturb a sample to increase its likelihood most rapidly. And so you could imagine a basic procedure where an MCMC kind of procedure that, like what we talked about before, where you initialize a particles at random. And here I'm showing multiple particles, but you could imagine sampling x0 based on some initial distribution. Then you could imagine repeatedly kind of taking this update where you're basically taking a step in the direction of the estimated gradient. So you just do gradient ascent on using the estimated scores to decide the direction. And if you do that, you can you're gonna get something like this, where the particles kind of will all converge in this local optima, the local maxima, hopefully, of this density. Which is kind of right. Like you can imagine, you start with random noise, which is an image which is pure noise, and then you follow the gradient, and then until you reach a local optimum where you can no longer improve. We know that that's not the right way to generate a sample. The right way to generate a sample is to follow the noisy gradient. That's what we call Langevin MCMC, which is exactly the same procedure, except that we also add a little bit of Gaussian noise at every step. And if you do that, then you'll see that we'll actually generate, and you run it for long enough, this procedure is guaranteed to produce samples from the underlying density. So remember that this vector field corresponded to a density where we have a lot of probability mass here, a lot of probability mass there. And indeed, if you look at the distribution of these particles, they're going to have the right distribution. Because what we've seen is that this Langevin dynamics sampling is a valid MCMC procedure in the limit. So it's a way of sampling from a density when you only have access to the score. So we know that if you initialize your particle, it doesn't matter how you do it, and then you repeat this process of following the noisy gradient in the limit of small step sizes and infinite number of steps, this will give you a sample from the underlying density. So literally all we're doing is replacing the true score function with the estimated score function. And basically that's one way of generating samples. You first estimate the score by score matching, trying to match this, have this neural network output arrows, output gradients that are close to the true one, and then you just follow the directions. And to the extent that you've done a good job at estimating the gradient, and to the extent that these technical conditions are satisfied, this would produce a valid sample. And so that's basically the full picture. The full pipeline is you start with data, you estimate the score, and you generate samples by basically following the score, which kind of corresponds to removing noise. Right? Because we know that the score is telling you the direction that you should follow if you want to remove noise. And so back to what we were discussing before, it has a little bit of this flavor of removing noise and then adding noise, because that's what Langevin is telling you to do. And unfortunately, if you just do this, it doesn't work. So this is what you get if you use this procedure. You try to train a model on MNIST, even simple data set MNIST, LBA, CFR10. It just doesn't work. And kind of like this is what the Langevin procedure looks like. You start with pure noise and then kind of get stuck somewhere. But it doesn't produce good samples. And there are several reasons for this. One is that basically real world data tends to basically lie on a manifold. So, and if the data is really on a manifold, the score might not be defined. And you can kind of see this intuitively, like imagine you have a density that is sort of like kind of concentrated on a ring. As you make the ring thinner and thinner, the magnitude of the gradient gets bigger and bigger, and at some point it becomes kind of undefined. And so that's a problem. And indeed, real data tends to lie on low-dimensional manifolds. Like if you just take MNIST samples and then you take the first 595 PCA components, so you project it down on a linear manifold of dimension 595, there is almost no difference. So it basically means that indeed, even just if you restrict yourself to linear manifolds that you can get with PCA, there is almost no loss. And if you take CIFAR10 and you take a 2,165 dimension manifold, again, almost no difference after you project the data. So seems like indeed that's an issue, and you can kind of see, like if you look at the training curve on CIFAR10, the slice score matching loss, it's very, very bumpy and it doesn't quite train. The other issue, which was kind of hinted at before, is that if you think about it, we're going to have problems in the low data density regions. Because if you think about points that are likely under the data distribution, we're kind of going to get a lot of samples from those regions. Like if you think about the loss is an expectation with respect to the data distribution of the difference between the estimated gradient and the true gradient. But when this expectation, we're approximating it with a sample average, and most of our samples are going to come, let's say, are going to be up here and are going to be down here. Like we're never going to see samples in between. And so if you think about the loss, the neural network is going to have a pretty hard time estimating the gradients in between. And you can see here an example where we have the true data scores in the middle panel and the estimated data scores on the right panel. And you can see that the arrows, they match pretty well at the corners where we're going to see a lot of training data, but they're pretty bad the moment you go away from the high data density regions.
Is there some way you could, when you're doing this on CMC, to want smaller vector field directly? So like if you sample the whole thing, it'll be like, oh wait, the bottom corner and the top right corner have really small arrows, so then I want more there. So then just genetically put more there, and then it's...
Yeah, the problem is how do you find it? And I guess one way to try to go to you're trying to find stationary points, or you're trying to maximize, I guess, the log likelihood. And it's not obvious how you would do it. You could do gradient ascent and try to find a local maximum. But the problem is that the gradient is not estimated accurately. If you imagine randomly initializing a data point, very likely you're going to be initializing in the red region, and then you're going to follow the gradients, but the gradients are not accurate because they're estimated very inaccurately, and then your Langevin dynamics procedure will get lost, basically. That's kind of like what happens is that, if you think about those particles, a lot of those particles starts out here, and you're going to follow these arrows, but the arrows are pointing you in the wrong direction. So you're never going to be able to reach these high data density regions by following the wrong instructions somehow. Yeah.
What if we just initialize at one of our data points? Would that help?
You could try to initialize to one of the data points. The problem is that still then it's not going to mix, which is kind of like what's going to come up next. That even though Langevin dynamics in theory converges, it can take a very long time. And you can kind of see the extreme case here, where if you have a data density that is kind of like a mixture of two distributions, where the mixture weights are pi and 1 minus pi, but crucially P1 and P2 have disjoint supports. And so basically you have probability pi1, pp1 when you are in A, and you have 1 minus pi p2 when you are in B. So there's two sets, there are disjoints, and you have kind of like a mixture of two distributions that are with disjoint supports. Think of like a mixture of two uniform distributions with two disjoint supports. Like if you look at the score function, you'll see it has this expression. It's just the log of this in the support of the first distribution and the log of this in the support of the second distribution. And you can see that when you take the gradient with respect to x, the pi disappears. So it does not depend on the weight that you put on of the two mixture modes. And so that's kind of like the problem here, is that the score function does not depend on the weighting coefficient at all. And so if you were to sample just using the score function, you would not be able to recover what is the relative probability that you assign to the first mode versus the second mode. This is kind of like an extreme case of Langevin not even mixing, basically. Yeah, basically, if you run a Langevin, it will not reflect pi. And here you can see an example of this, where the true samples, there's more samples up here than down here. So this let's say P1 is maybe, I don't know, 2/3 of them are up here and 1/3 are down here. If you just run Langevin, you kind of end up with half and half. So it's not reflecting the right weight. And that's basically an indication that, again, sort of like Langevin is mixing too slowly. And yeah, then what we'll see in the next lecture is a way to fix it that will actually make it work. And that's kind of like the idea behind diffusion models, which is to essentially figure out a way to estimate these scores more accurately all over the space and get better guidance. And that will actually fix this problem and will get you the state-of-the-art sort of like diffusion models.